Okay, today we'll look at memory design today and the next few lectures. And we'll start off with static random access memories. Memories or memory arrays can be categorized into three different classes based on how you access the contents of the memory. First is the random access memory, where the contents of the memory are basically accessible randomly based on the address you give. So this is like accessing an array using an array index. If you have written any script or a program, you have an array of words and then just you give the index and you get the word corresponding to that. So that is basically random access memory. Serial access memory is you can access the contents of the memory in a sequential fashion. And content accessible memory is a memory where to access the contents of the memory you have to give a piece of the data which is already there in the memory. Remember, you give pieces, not the whole data, because if you have the whole data, then what is the point of looking up in the memory? But you have a piece of the data and you want to get the attached associated content along with that. So we look at all these different memories over the next few lectures. Now within the memories, so I would not classify it, here random access memory is either volatile or non-volatile, but in general any memory, even serial or content, the memory can be volatile or non-volatile. What does it mean? Volatile memory is a memory which holds information only as long as you apply power to it. As soon as you disconnect the power supply from the memory, the content goes away. It's volatile. Non-volatile is it remains. The memory remains even if you remove power. Okay. So, for example, the cave paintings in Ajanta caves, right? That is a non-volatile memory. There is no power, but information is there. The drawings are there on the walls. Okay. Or your hard drive. You disconnect the hard drive from power supply, but you put it back, it's still there. Or your flash memory or your USB sticks. All those are non-volatile memories. Now within the non-volatile memory, you have various kinds of non-volatile memories based on the actual technologies used to store the non-volatile information. We will kind of probably look at one of these later in one of the coming lectures. And for the volatile memory, there are basically two classes: static memories and dynamic memories. Static memories are memories where information remains in the memory as long as power is there. Volatile static memory. Power, you have to give power, but you don't have to do anything else. As long as power is connected, it maintains information. So that is a static memory. Whereas a dynamic memory is, even if you have power, it can leak away. So periodically you need to refresh. So dynamic memories or DRAMs, dynamic random access memories, are what are used for the main memory of all your computers, right? Cell phones, computers, etc. The main memory is, at least the desktops and laptops, the main memory is the DRAM memory. And static RAM memories are memories which are usually used inside a chip. Memories which are inside a chip are made out of static RAM memories. Though we will see people are also starting to put dynamic RAM memories embedded inside chips. And of course, for serial access, you have various kinds: serial in, parallel out, parallel in, serial out. And then you can structure them in the form of queues: first in, first out, last in, first out. Today we'll start off looking at serial access memories, as it will also be useful for you, perhaps both serial and random access, SRAMs. It might be useful for your projects also. Okay. So first let's look at the memory element, the static memory element. Okay. Static because if you write data into it, if you store data, it remains as long as you put power to it. So we are only talking of volatile memories. Non-volatile memories require special processing support. You need to have additional process steps for you to be able to make the non-volatile memory. If you want to just make a memory in a vanilla process, in a standard CMOS process, then it will have to be a volatile memory, and it can either be a static or a dynamic memory. And static memory makes your life easier as a designer. The design using a static memory is much simpler because you don't have to worry about information leaking away, periodically refreshing, and so on. Okay, so you have already seen this static memory element. What is this? Now this is the latch, right? This is the sequencing element, which is the latch. And really the key here as far as storing information goes is this loop out here. You see there are two inverters. Of course, this is a funny inverter. It has this additional inputs phi and phi bar, which is essentially a tri-statable inverter. But when this memory element is holding information, okay, that time phi is 0, phi bar is 1. That is, enable is 1, enable bar is 0. That means both this NMOS and PMOS both are on. That means this is just like an inverter. So really what you have is when it's holding information, you have two inverters connected back to each other. It's like a loop. It's a positive feedback. It reinforces each other. The two nodes, here there is X, let's call this Y. If X is 0, Y is 1 because of this inversion, and then when Y is 1, this is 0 because of this inversion. So it is a consistent, self-consistent setup. It's a stable situation. Similarly, X can be 1, Y can be 0. So both 0 and 1 information can be stored in this loop. And because you have two inverters driving this, each of these nodes is firmly held to their respective voltage values. So that is why it is a static element, because it's held. So it's a very robust memory element. It kind of retains information robustly.
What do you mean by firmly held?
What I mean by firmly held is in contrast to not having this feedback loop. Just imagine that you didn't have this feedback loop. You removed these two inverters. Okay. Now what you have is you have X here. The transmission gate connects to X, which just connects to this inverter and goes on. Now when this transmission gate is off, okay, this node here is essentially a floating node. No one is driving that node to any particular value. It will have some voltage left over from when this was on, and then it will hold the voltage. But that voltage is not firmly held because no one is holding that voltage in that node. It's just some capacitor, it has some charge, it remains there. Now what will happen is that charge will slowly leak away because you will have subthreshold, this transmission gate is off, so you will have subthreshold leakage through this. You will have gate leakage out here. You have PMOS and NMOS, both have gate leakages. You will have leakage. You have diodes out here. You see these two junctions, they are diodes. You will have leakage through those diodes. In addition, if you have any signals, you will have coupling capacitance to this node. So when those signals switch, charge will get injected. So the value of X is not firmly held. I mean, it can get disturbed easily and then it remains disturbed. Whereas here, when you have this feedback out here, even if it gets disturbed, as long as it doesn't switch the state of this memory cell, it gets restored back. So that is why having this feedback helps to staticize the node, make it static. Otherwise, it would be a dynamic memory element. Now you see there are two additional things out here. One is a way to write information into this node. That is done through this. Essentially a transmission gate, which allows you, when transmission gate is turned on, that is when phi is 1, NMOS is on, PMOS is also on, and so this inverter is connected to the X. So whatever happens to D happens to X with an inversion, logical inversion. And then when phi is 0, you disconnect X from here, so now you are isolated that one. What this tri-state inverter does is that you operate the tri-state inverter with the opposite polarity to this transmission gate. You only want one person to drive that node X. so that there is no fight. So when you want to write data into the X, you disconnect or you make this transmission gate into high impedance. So when you turn this transmission gate on, these two are made off. How? Just by connecting the appropriate polarity. Phi you connect, when here phi is connected to NMOS, whereas phi is connected to PMOS here. So when phi goes high, this NMOS turns on, this PMOS turns off. Similarly, phi bar goes low, when phi goes high, phi bar goes low, so this PMOS also turns on, but phi bar is connected to this NMOS, so this NMOS also turns off. So this tri-state becomes high impedance state. So this is no longer able to influence this X, only information from here gets written in. So X will follow D. And then once you finish writing, you disconnect this and then turn this on so that you close the feedback loop, it will hold the data robustly. Okay, so this is how you write into this mode. You can write both 0 or 1, easily with this structure. And when you read out this, you just have a simple inverter which Q becomes X bar, which becomes same as D. So you have a non-inversion. So you can read this node X. So this is the basic this is the basic memory element, which is kind of like the workhorse for all internal memories.
So why can't we get the output from what you earlier mentioned as Y?
Correct. So the question is, why can't you tap output from Y itself? Say this is, if you call this node Y, why not just take this out? Maybe just relabel this as Q. And you can do that, so that way you save one extra inverter. Now what happens is that, if you know how you are going to use this latch, what is the scenario in the output? You can definitely do that. Similarly, you can also say, why have this inverter? You can remove that inverter also. Okay. Now, what is the danger of doing that? The danger is when you don't know how this particular latch is going to be used. Okay, in what is the environment around it. Then exposing these internal nodes to the external environment can be kind of dangerous from the point of view of perturbing, because see, these are the important nodes. If a lot of noise gets coupled, then it will disturb the state. So that is where you have these buffers used to buffer and isolate these sensitive internal nodes from the outside world. But if you know for sure what is the environment around it, and you are sure that no extra noise and so on will come, then you definitely can remove both these two inverters. Okay, especially when you are putting these in a context of an array, when you have lots of these, then even saving 2 transistors from each of them means you will save a lot of area. So there you can kind of basically optimize further. Similarly, you will also see designs where in this feedback the tri-state is replaced by a simple inverter. Okay, the reason to do that is so you can eliminate these 2 transistors. So it becomes a simple inverter. Now what is the negative of doing that? The negative is that when you want to write into the cell, then this node X is being driven by this inverter, as well as when the transmission gate is on, by this inverter and the transmission gate. So both are driving that node X. Now you always, so there is a fight, because suppose this inverter is driving a value opposite to what is being you want to write, and then there is a fight. Okay, but if you can ensure that the writing person always wins no matter what the process condition is, then it is still okay. Because for momentarily there will be a fight, but then this particular path is sized bigger to always win that fight, and then once he wins it, this will also follow. You just force it. The advantage of doing that is you have reduced 2 more transistors from this, and you can reduce the area. Okay, but you have to be careful in doing the design and ensure that this write will always happen under all kinds of process shifts, process variations. Remember, we said we can have process variations where transistors can be mismatched. Even though you might have same size transistors, the drive strengths can vary randomly. So you have to overcome that by sizing these appropriately, by making sure that they are sized bigger so that this will always win. And at the same time, maybe even sizing this, weakening this, perhaps using longer than minimum channel lengths and so on. So you weaken this feedback so that you ensure this wins, and then you can remove these two inverters. Whereas a design like this is fairly, you don't have to think too much about optimizing the design from the point of view of ensuring robustness. It's kind of fairly robust design, but you pay the price of a lot of transistors. As soon as you start removing transistors, you have to do more and more analysis to ensure that it will work under all conditions. And the flip-flop is just putting these two latches together. Okay, a flip-flop is edge trigger, whereas a latch is not edge trigger. It's a level sensitive design. When the transmission gate is on, D comes, Q follows D. Only when you close the transmission gate does the latch hold the information. By putting two of these back to back and then operating them with inverted clocks, you obtain an edge triggered operation, because you have the master latch and you have the slave latch. Okay, you notice here in the slave latch we have removed this inverter. There is no need, because it's protected, it's kind of inside, this can itself drive. So we don't need that. We don't need the input inverter here, and we don't need the output inverter from this latch. So both of those have been removed. So you have this master latch and the slave latch, and they operate in a ping pong fashion. When master is transparent, slave is opaque. And when the clock goes from 0 to 1, master goes to opaque, slave becomes transparent. And so the data of the master comes into the slave and goes out. So only at the rising edge of phi or phi, basically you have the output. Now these flip-flops are kind of the workhorses of synchronous designs. The thing with the flip-flop is that you can easily chain them without, you have to pay a little bit of attention, and I'll come to that, something called hold time. But you can chain them and then things will work properly. With the case of a latch, you have to be very careful when you chain the latches, because a latch is transparent for a duration, maybe half the clock cycle. When you chain them, then you have to ensure that the two latches which are next to each other, like a latch 1 feeds the latch 2, they don't become transparent at the same time. Because when they are transparent at the same time, then you have a race through. Data can just go from one to the next during that portion. You don't want that to happen. So usually when you chain latches, they are put such that opposite polarities are used. For example, here we have chained two latches, but they are transparent on opposite phases of the clock. So this is how you need to chain the latches. So this group is called a flip-flop, and now I can put as many flip-flops as I want in a chain to form shift registers. So these shift registers are basically what are used for making serial access memories. Okay, so here what we have done is we have just put a chain of flip-flops. All of them are triggered by the same clock. Okay, there is an additional signal set and clear. We'll not worry about that right now. By putting, essentially it allows you to, when clear means it will put a 0, Q will take a value 0. When set is set, you have a 1 in the set signal, Q becomes 1. So there's some additional circuitry inside the flop which will give you either 0 or 1. But the important thing is the data input to a flop comes from the Q output of the previous flop. Okay, so now what happens is that when you have every edge of the clock, you put in a new value of D from D to Q0. Okay, and Q0 goes to Q1, Q1 goes to Q2, Q2 goes to Q3. You are shifting everything by 1. Every clock edge you shift everything by 1 cell to the right. So here, for example, you see what you have is I have my data which goes from 0 to 1 here just before the clock edge happens. And so this 1 comes into Q0. Q0 becomes 1 and everything is 0. The next clock edge data has gone to 0. So I shift a 0 into Q0, but what was there in Q0 shifts to Q1 and so on. So it has shifted right by 1 bit. So I have 0, 1, 0, 0. Here in this clock edge, it's not aligned properly, but in this clock edge I shift in a 0 because just before the clock edge my data was 0. So I shift in a 0 and everything shifts right, so I have 0, 0, 1, 0. In this clock edge I have 1, so I shift in a 1 and then these shifts right by 1. And then again here I shift in a 1, so I have 1, 1, 0, 0. So you see I'm shifting 1 bit at a time. So this also, so now if I just look at Q3 and ignore the others, then it's just a shift serial in, serial out. Okay, but typically in these shift registers we are also interested in many applications to get the data out, Q0 till Q3. So what you do is, if you want to set up a particular bit pattern, let us say I want to have the bit pattern of 1100, then over a number of clock cycles you can toggle D such that you have a pattern 1100 out here, and then you are done. So you have 1100 pattern now set up across this. So you see it has taken basically 4 plus 1, 5 cycles to set up a particular pattern. Basically it takes 4 cycles to set up any pattern you want. So you pay, you have to spend extra time, as opposed to something suppose you had a random access memory where you could randomly select one of these flip-flops and write a value, then you can do it in a single cycle. You give the address, you select, you write it, and you're done. Whereas here it takes more cycles to set up the pattern because you have to go one by one. Benefit of this is very simple, in the sense that your inputs, you just have one data input wire, of course clock is one, that's it, but you need to have some state machine which is counting and keeping track. So area overhead at this portion is small, but you push the complexity to something else sitting outside. But a lot of places this kind of thing is very useful. For example, in testing, in manufacturing test of a chip, when you have a combinational logic block, you would like to put in a particular test pattern and look at the output of that combinational logic block and analyze and see if it is okay. That way you can detect a lot of the faults, because when you manufacture the chip, maybe there is a short between a pair of wires, maybe some wire is stuck at VDD, maybe there is a short to ground, maybe there is an open, some wire is not formed properly. To check all these kinds of errors, manufacturing defects, how do you check it? You have to put in a pattern and see if the right output comes. Right? For example, if AND gate doesn't have a connection to VDD, then when you give a 1-1, you will never get a 1 out, because there is no connection to VDD, it will never pull it up. So you can check that by putting 1-1 and checking if the output goes to 1. If it doesn't go to 1, you know there is a problem. So like that you can identify test patterns. Now these test patterns are introduced in the serial fashion. You have a shift register where you just shift in the test pattern, then this becomes the input to your combinational logic block, which gets tested. Similarly, at the output of the combinational logic block, the parallel outputs are captured in a register and shifted out serially. So now you just have a single extra pin through which you can put in all your test patterns and take it out. Things are a little bit more complicated, but basically this is the main idea of shifting in serially and taking out, essentially to reduce the pin count. Okay. Now one of the problems with this is that, as you are shifting in, what is happening is this Q0, Q1, Q2, Q3, they are changing. Now sometimes it's kind of not nice. Okay, you have a certain pattern which you are happy with, now you want to change to another pattern. But to change it, you need to keep shifting things. And for those clock cycles, these patterns are all changing, Q1, Q, everything is toggling. And that can be a problem. For example, whenever you are toggling exactly, you have activity, which means power consumption goes up. All the toggling is exposed, because if you have a combinational logic which is seeing that, Everything is just toggling unnecessarily, and it's a waste because you really don't care about these intermediate patterns. You are just going from one to the other. So to prevent that, sometimes you can, well, what you have to do is you have to have one more level of registers. This is also called a register, by the way, a flop or a register. So you, for example, you can use what is called an enabled flop. So this is the symbol where only if there is an enable will Q follow, or will the positive edge have an effect. Otherwise Q will remain whatever it was. So you can implement it in two ways. Either this way, where what you have is the output is recirculated back to the input. If load enable of this enable is 0, then only D will always see Q. So the same value keeps getting recirculated. As long as enable is low, the same value keeps getting circulated. Only when enable goes high will a new value get registered by this. Another way of doing that is to suppress the clock here. So you have load enable coming here, gated with this clock.
How does this help in reducing the toggling?
Next slide. So we'll get to that, how you'll use this to reduce the toggling. But the point here is that there are two ways of doing this enable. And this way we have already seen, this is what is done for a gated clock. And you just have to be careful in making sure enable is properly, so that you don't have glitches in this signal out here. You have to make sure enable doesn't toggle at all random times. Okay, so it has to be latched with respect to clock. The benefit of this approach is that you don't have any, when I'm not loading this flop, I don't have any transitions here. So power is less. Whereas here it's much, in some sense it's, here my clock will always keep on toggling. But my, so I'll have more power consumption here. So now let's come back to our problem. So we had the original shift register. So now what we do is, we have this data and this is the final parallel data we are concerned with. We'll isolate that from the internals of the shift register by this bank of flops. So here there will be a load enable. So once after I shift it, my load enable will go high, and then this data gets captured into this. Then it comes out. So basically what it means is you need to have a controller which can orchestrate all these things. There is a little controller which is orchestrating and making sure you have the load enable goes at the right time and so on.
So the supply band is always closed.
Pardon?
The supply band means the signals of flip flops. Lower level flip flops are always stored according to the bits entering the flip flops. Only the upper level flip flops only will be changing with the enable.
That is right. The lower one will not change with the enable because there is no enable here, but the upper one will change with the enable. Yes.
But it doesn't change the activity factor for the lower one.
Lower one it doesn't change. Yes. But remember what we are saying is the Q0 to Q3 are connected to some combinational logic block. So now in the inputs to those blocks are not changing while you are shifting out here. That is what we are concerned with. While you are shifting, you had all these patterns. Hey, I wanted 1100, but I went from 000 to 1 to 0100. All this, we had all these transitions which were happening, which have been eliminated now. So nothing is happening in the combinational block, whatever is connected to here. Okay. So you do this only if you want, if you're concerned about power, or maybe there are certain other reasons. For example, you're controlling some circuitry out here, and this Q0 to Q3, there are only certain bit patterns which are valid bit patterns to that control circuit. And while you're going from one valid pattern to another, when you do the serial shifting, you go through a lot of these intermediate states which are not valid states, or which will just put the whatever you are doing into a wrong state. Then you will be in trouble. For example, one of these bits could be going and controlling the power down signal, of your some piece of logic. Maybe you have some analog circuitry, there is a bias. Bias enable is controlled by one of these things. So you want to change states from one state to another, but without shutting off the bias enable, because you want the circuitry to be on, but you want to change the configuration. So this gives you that protection, because you go from one valid state to next valid state. Now, one of the important things when you have the shift registers which you need to worry about is these hold time violations. Let me just explain. So we saw the setup time issue, right? Setup time means when clock edge happens. Remember, these are edge triggered flops. That means a positive, here it's a positive edge triggered. If I put a bubble, it becomes negative edge triggered. When a positive edge happens, I capture whatever was there at D input and put it to Q output. But what is there in the D input has to have settled for some time, at least some minimum time before the edge happens. That is called the setup time. If it comes too close to the edge, I don't get the right value. Now hold time is, even after the edge has happened, I want to hold the value of D for some time. I should not take it out quickly. Just because the edge has happened, I should not take it out. So that extra amount of time I need to hold the value of D is called the hold time. So, for example, here we have these two flops in a shift register. I've just called these nodes C1 and C2, because usually these problems happen, or they are exacerbated when there is a skew. C1 and C2 are supposed to be the same clock happening at the same time, but maybe these flops are kind of far apart and there is some wire from here to here and something, whatever, and then there's a little bit of delay difference as to when an edge happens for this flop versus this flop. That's why I call them C1 and C2. So here C1, C2 goes high, D1 goes from 0 to 1, Q1 becomes 1. And Q1 is the same as D2, so D2 goes 1. And let us say, you see what happens to Q2. Q2 captures the previous value. Previous value was 0, so Q2 becomes 0. Now in the next edge, D1 goes low, so Q1 also goes low. But D2, which was high, is supposed to come to Q2, which is what is the right thing, right? D2 was high, so in the next edge, Q2 should be high. But just imagine that due to some reason, C2 gets delayed. Maybe you have wired it in a certain way that C2 comes a little later. It gets delayed. And Q1 and D2 happen a little earlier. So before C2 could capture the old value of D2, D2 changes. D2 becomes 0, and instead of capturing a 1, you become 0. So this is called hold violation, because you have been very urgent in changing D2. Okay. D2 should have held its value for a little bit of more time, and it didn't, and so you have captured the wrong value out here. That is called hold violation. These hold violations are very troublesome. See, with setup violations, where you have to ensure that the data comes well ahead of time. If it fails, suppose due to some issue you fail the setup, you can always slow down the clock. You can increase the clock period a little bit, and beyond a certain clock period it will start working. There is no problem. Whereas if you have a hold time violation, you cannot do, no such thing will help. You cannot, changing the clock period will not help, because the problem is a problem of these two edges. There is a mismatch. Pardon? Exactly. So what you need to do is, it's happening too fast. So this hold time violation has to be fixed by introducing what are called delays, buffers. So these are essentially, in the industry parlance, hold time fixes where buffers are put. So after the design is done, and this problem can happen even when essentially it happens for fast paths. Really the fastest paths, because you see this cannot be the critical path in your design, because it's just a piece of wire. Critical paths don't have this problem. It's really the fast paths. So you have to slow down the fast paths by introducing delays to fix the hold time problem.
Sir, what are the things on which setup time and hold time depends? How can you say that these devices will have this much setup time?
Right. So what we'll discuss that when we discuss about flops and so on, the sequencing elements in a little bit more detail. Basically, it has got to do with the internal circuits of the flop. So just to kind of give you a quick preview out here, you see, for me to capture the value, I need to be able to overturn this and get it to a point where this I can trip this. Suppose I want to write a new value, I need to be able to trip this, get it to a certain point where it will capture that value. And to get it to that point, this data has to go through this inverter and this transmission gate and charge up or charge down this capacitor. So finally it comes down to delays in this path out here. How much capacitance is there in this node? What is the sizing of these? So that kind of determines your setup hold times.
Setup time will be determined by charge. And hold time will be.
See, they are kind of related basically. Hold time, see, there is also this if you see, hold time problem comes when things happen too fast. So, for example, you might have a slow charging but fast discharging perhaps. So, again you can have, so that could lead to a problem with the hold time. Essentially, it has got to do with how quickly you change the state of that node X. Okay, so now when I use a flop versus a latch, the thing is, again, this is for you to keep in mind. A latch and flop both store information. It's just one bit of information, except if you see in a flop there are two latches. So in some sense you are paying a price, you are doubling the area to still hold one bit of information. But the benefit of a flop is that your design, everything kind of becomes much simpler. It's an edge trigger design. And so generally, it's kind of much simpler to close timing and have a robust design. But of late, if you see, industry is moving to more latch based designs, and some advances have happened in the tools, because again, with digital design you have to rely on the tools at the end of the day. Small designs you can do by hand and so on, but really the designs have millions and millions of gates, so all methodology has to be incorporated in the design tools. Only if the design tools support, then we can do. So now you can start doing latch based design. But remember, when you don't have these problems of hold time and so on, you should definitely think of using a latch or latch type of structure where you optimize and reduce the number of transistors. Okay. So parallel in, serial out, pretty straightforward again. What you have is you have P0 to P3 coming in, and you have this load control signal which sets the mux to take the data from the parallel input port. So one cycle you take the data from the parallel input port, and then the subsequent cycles you set the mux to point to the shifting thing. So then you shift out the data. So that was serial memories, right? Now in the case of random access memories, what you have is you have, so here you might so you have words out here and you have rows of these words. So in a random access memory, you, based on the address, you have an address which you break up into two pieces, one to select the row and the other to select the column. So you can access a particular specific bit. So no matter what bit you are accessing, the access time is same. Unlike in a serial memory. Serial memory, if you are accessing the last bit, you get it right away. With 0, you don't even have to do anything, it's already there. The one before it takes one cycle, and so on, 2, 3, 4, etc. Till the access time is variable depending on where the bit is in the sequence. In the case of random access memory, it's a fixed access time, independent of which memory word you are accessing or which memory bit you are accessing. So when you arrange it in this fashion, you have a decoder which here, for example, there's 2 to the n minus k rows. 1, 2, 3, 4, 5. So there are 8 rows out here, and he is taking out 4 bits. There are 8 rows and 8 columns. So you take 3 bits to cell, and you decode it, and you activate one of these horizontal lines. Those are called word lines. You activate one of them. When you activate one of them, what happens is the data in these square boxes, which is the cell, memory cells, gets transferred onto this vertical lines, which are called the bit lines. So say this top row gets activated, that means that word line becomes active. The contents of each of these cells get transferred to the respective vertical lines, which are called the bit lines. Now from these 8 bit lines, here the memory has 4 bit output. So you have a 2:1 mux. You choose one of these pair of bit lines and get the data out. So you have an additional 1 bit to select which of the pair of bit lines you have to connect to the output. So you break up the decoding problem into 2 pieces. Row decoding to select the row and column decoding to select the column. And now you can access any 4 bit chunk here, any 4 bit word in a constant time, regardless of what the address is. So of course, what is the penalty is this: you have this extra decoding area has to be put in to decode and get it. So now if you look at the row decoder is basically, if you take a 4 to 16 row decoder, then you have the 4 bits, and then corresponding to the 4 bits, one of the 16 word lines gets activated. So all possible bit and bit bar complements you have to combine. So you have A0, A0 bar, A1, A1 bar, A2, A2. So there are 2 choices for each bit. So you pick one of the 2 in each of these, for each of these 4 input AND gates, and you get all 16 combinations. This is a 4 input AND gate which has been implemented as a sequence of 2 input NAND gates. This is a NAND NOR structure. If you push the bubble on this side, it becomes a NOR. So this is really a NOR gate which is just written this way, so that it becomes easy to see that it's a 4 input AND function. Remember where we had discussed about logical efforts and so on. This is where that comes in. What structure to use? Should you use a 4 input AND gate, or should you use a NAND NOR, or should you do something else? So that's where logical effort comes in to kind of give you the right answer. Usually a NAND is a better, turns out to be the one with the lowest logical effort, and also turns out to be the fastest. So this is a NAND. This is still a NAND NOR, I guess. Yeah, still a NAND NOR. But here what they have done is they have taken these, they've done some sharing. Okay, instead of having so many NAND gates here, 32 NAND gates here, here all of them are pulled out and they are kind of shared in some sense. So this is called pre-decoding. Okay, what it does is, what you do is you take your address, you break it up into 2 groups. Each group has 2 bits. So this becomes a 2 to 4 decoder. This becomes a 2 to 4 decoder. So with this 2 to 4 decoder, one of these 4 lines become active, and with this 2 to 4, one of these 4 lines become active. And now you can combine one each from each group. So again you have 16 possibilities, all 16 are set up here. So this technique is called pre-decoding. Pre-decoding has the advantage, it turns out again to be the better way of doing decoding, where you can get faster decoders and lower power decoders. Mainly because if you go back out here you have very long wires, and no matter what the address bits are, you'll always have 4 long wires switching, because for each address bit one of these 2 will switch from 0 to 1, again same here. Whereas here, because you did the pre-decoding, these long wires, only one of this 4 will switch and one of this 4 will switch. You'll have only 2 wires switching. So activity is reduced on these long wires. So pre-decoding is the preferred option. Turns out even for speed it's better. Power also it is good. So now let's just look at this complete say lookup table, right? You have for your project you have a 16 entry lookup table. So you have some memory elements. Let us say for now you use the latch. Okay, the latch has this. I put the T out here because you don't want to use a flop. A latch is good enough for something like this. You don't, and you have so that you have less area. And the latch has I label this T, which is where the clock input comes. So you have 16 such entries. Now you have a row decoder. Okay, you have a 4-bit which comes in, which is what you use to do your logic lookup. That gets decoded, and when you want to do a write, so something is missing here. But if I want to do a write enable is missing. If I want to write here, I can randomly write into one of these. If I don't want to write, I don't want to turn on these things, any of these clock inputs. The same data is given to all of them, all the 16, because I know I'm going to write only on one of them. So only one of these horizontal lines should get active based on this address. Similarly, when I want to read, I just set the mux to pick up one of these 16. So write enable signal is missing here. Okay, sorry. So if you do that, then you'll have a 16 entry lookup table using. So now the thing is, the write, can it be done serially is the question, and of course you can do it serially also.
In this case, it is serially, right? Because at one time only one flip-flop is activated, so you don't have to.
If we, serial, not in that sense. Yes, of course, I can never write. You can only write one memory entry at a time, whether it's a random access memory or a serial. We are not, when you say serial versus random access, that's not what we are saying. If I want to write, for example, the 16th entry versus the first entry, how many cycles does it take? In a random access memory, is the same time, whether I write the 16th entry or the first entry. Whereas in a serial memory, you shift serially. Okay. Now, when you shift serially, what you have to be, you are disturbing the contents of the memory. Suppose I want to write some 4th location. So how do you do it? If you shift it, everything gets shifted. So you have to take care to make sure only, you have to do some, you can do it, it's not such a big deal, but you have to figure out exactly how to do it, such that only the 4th entry, after all the shifting and everything is done, only the 4th entry has changed, everything has remained where it is. That I'll let you figure it out as part of your project. It's not that hard, but you should figure it out. But you have a choice. You can do, that's why I'm kind of covering this. You can have either random access or serial access. Random access means more hardware, but simpler control. Serial access is less hardware, but more complicated control.
So what is that clock?
Yeah, this should have been a write enable signal. It should have been write enable signal. And also the clock is there because I've used a latch type structure out here. A latch means it is transparent for some time and then it is opaque. So what I need here is, when I write into a particular entry in the memory, this word line has to be like a pulse. It has to go on and then shut off. And I'm creating that pulse by just ANDing. Finally, what you'll do is you'll just AND it with the clock, because clock already is like a pulse. Of course, the pulse width is exactly 50% of the clock period most of the time. But that is there. I don't have to do anything extra. So really, all you do is you AND the clock. Clock becomes another signal to your decoder. So you can AND it. Here there is no counter. See, because this is a random access. Whatever address is there, 4-bit address, the appropriate word line gets activated.
Then why we need clock?
Because the word line I want to go high and come down. Right. So if I want that pulsing in the word line, then I have to AND it with, I have to create that pulse. Now, whether you need it for this particular case, suppose you don't have that. So then what happens?
Always it's on. If clock is not there, then always on.
It is always on. But you definitely need a write enable signal.
So that will function. If we have the right enable, we need not.
Then you don't need to have the clock. clock, exactly. So then what will happen is one of them is always in a transparent phase. The selected one, you always have one word line which is always on, so that latch is transparent. So whatever data is there will come out. If for some reason that data changes, because maybe that wire is connected to something else, then you are in trouble. So that is why it's good to have a very clear notion that when I do a write, there's one cycle where I do a write because I have write enable asserted. After that, once the write enable goes away, I don't have that. Now I can achieve that by having the write enable go high and come down for that cycle. So then you put it always in the read mode. The memory is always in the read mode. When you want to write, you turn it on for that one cycle, it writes, then you can do it that way. So instead of a clock, you can have the write enable come that. Yes.
So whenever I am writing, that time I want to be disabling my reading section.
No, there's nothing to do.
Most of the time, the unable symbols of read slash write. The same thing is.
Yes,
Either I can read or write.
correct. Now, typically when you use it, especially when you're writing, in this case, what will happen? The same address is given to both. So whatever you are writing will also come out. So in that sense, it's not a much use. I mean, in the sense that, I'll get the same thing back. So this is a very simple structure, right? It's just a mux. Now, if you had more complicated, where you had we'll see that next, send SAMs and so on, then you definitely, there's no need activating all that circuitry because you're just wasting power. Similarly, here, if you don't want to waste the power to drive this queue, you might want to disable that by ANDing it. Yeah.
So the row decoder, is it like at any given time, any of those lines, output lines will be high? Is it that?
Right, so let's go back to this, right? So if you see this decoder, it will be simpler out here. So this is a purely combinational logic. Whatever is the bit pattern, that corresponding word line will be high. It's just a combinational logic. If, for example, if I have all zeros, then all these will be ones, and so the first word zero will be high. It will just remain high continuously. Yeah. All we are saying is, if I want to do write, then I'll have an additional input out here in this AND gate. Instead of being a 4 input AND gate, I'll have a 5 input AND gate, and then I'll have the write enable going to all of them. Of course, from a design perspective, you can ask, is that a good way? Where should you do that ANDing function? Should you do it here? Should you do it somewhere else? For example, instead of having maybe I'll have a 3 input AND gate, NAND gate here, and the write enable comes here. Maybe. Right? So there is a choice from a circuit of how you implement it, but functionally you are just ANDing the address with the write enable signal, so that you only write only when write enable is high.
Though you don't want to write at a particular instant, clock will be coming high.
Correct. So so I don't need to put a clock here. In that case, I'll just put a write enable. Instead of a clock here, I'll put a write enable.
But then we may not have sync between when to write and D.
You have to maintain that sync. You cannot. That is not that hard to do. Write enable and D can come out of the same. There'll be another.
Clock.
Yes. So you will have a clock, because this will all be pipeline systems. So there'll be a clock which will give the write enable and the data for that write enable. So that has to be and the address to which you want to write. Everything will be synchronous. So there'll be a flop which is not shown. So now when you look at this latch, we said that we can optimize the latch by removing these two inverters, that inverter in the output and perhaps an inverter in the input. And so that's kind of what is done in some sense, but you see it's done in a kind of funny way out here. Basically, this is what a modern SRAM cell looks like. You still have two back-to-back inverters, because you see these are inverters. Output of one is connected to input of the other and vice versa. So it is still the same two inverters, except it's not, none of them are tri-stated. It's just two simple inverters connected back to back. And now access to this is provided from both sides. Okay, we'll see how that helps. And now what happens with this is that this, people have really figured out how to lay this out in a very, very optimized way. And this has become kind of pretty much the workhorse memory cell for large, whenever you have an SRAM, typically this is what is done. You have a memory cell which consists of these 6 transistors, 4 for the back-to-back inverters, 2 for access. Okay. If you recall the latch, of course, I mean it turns out that has 12 transistors, so now you have reduced it to 6. And these transistors are, a lot of engineering goes on to optimize the size, layout, everything. Certain design rules, layout rules are also bent to accommodate the SRAM, so that the SRAM size is made as tiny as possible. Because if you take modern chips now, pretty much the bulk of the area is spent for memory. You have logic, maybe processors, various hardware engines, and then most of it is memory. And memories are usually SRAMs, but now we have emerging coming technology as embedded DRAMs coming up, but largely they are SRAMs. So people have spent a lot of time optimizing the circuit of the SRAM and its layout. So layout is also very important. So let's look at the functioning of this, right? So now let us look at the read operation. Firstly, what we will see is there are these two inverters, and they are back-to-back inverters again. Okay. So they hold whatever state they hold it in a stable way. So let us say here Q is 0, Q bar is 1. Right? If Q bar is 1, see Q bar is connected to the input of this inverter. So Q is 0. So Q again goes to the input of the other inverter and Q bar is 1. So it's a self-fulfilling loop. And you have A1 and A2 as the access device to access the contents of the memory. Q and Q bar are the contents of the memory. So you will have some, say you want to read this memory cell. What is usually done is bit and bit bar are pre-charged high. They are pulled up to the high voltage. Say this is a 1 volt process like you are doing. You pre-charge bit and bit bar to 1 volt. You pre-charge it and let it go. That means you have a PMOS to pull it up and then disconnect the PMOS. So bit and bit bar become momentarily floating. Okay, this is an example where you want to use these kinds of dynamic structures because it turns out that it is worth doing that out here because of area reasons. So you charge bit and bit bar, the two capacitors are charged up and they are left floating. Then word line turns on. Word line goes from 0 to 1. Access devices A1 and A2 turn on. Now see, wherever Q is low, see in this example we said Q is low. When Q is low, what will happen is bit will start discharging through A1. Okay. So bit will start falling. But Q bar will remain where it is. So after, if you wait long enough, bit will fall all the way down to ground. So bit has taken the value of Q. So basically what you have done is you have transferred the 0 value from inside the cell to the outside. So that is basically how you do a read. If Q was 1 and Q bar was 0, then bit bar will discharge. So depending on the value, 1 of bit or bit bar discharges.
So why is the input and output?
In this case, the word line turns on, okay, to activate the cell. The cell access devices A1, A2 are the access transistors. So that is turned on. And now what happens is information which was stored in the memory cell comes out of the memory cell. Okay, if you look at information flow, whatever is there in the memory has come out onto the bit line. When I do a write, the reverse happens. From the bit line, information goes into the memory cell. So what is input output? It changes depending on whether you are doing a read or a write. That's because you are using a pass transistor. Charge can flow either direction. Right?
It depends on the strength.
Not the strength. Here there is, because see what you have done here is that bit is a floating capacitor. So it just discharges. No one is holding bit high. it just discharges through this access device A1. Okay, it might. We'll just go through the next few slides and then we'll. It might become.
For every SRAM, you will be having a pair of capacitors.
Exactly. So let's come back and look at the read circuitry. So what you have is you have these memory cells. So you have a column out here. Okay, let's go back and look at the array. In this array, of course, in this array only one line is shown out here. But really, what we have is you have a pair of bit lines. Okay, each cell has a pair of bit lines like this, and in this pair of bit lines, you have at the top of the bit lines, you have two PMOSes which precharge the bit line. Before a read, you precharge it and let it go to 1 volt or whatever is the VDD.
Even if you do not recharge, it would work, right?
We'll see why it will not work basically, but no, you have to precharge it. Okay, because we'll see that in a moment. But you have to precharge it, and it will discharge to whichever side of the memory cell had a 0. That bit line will discharge. Of the pair of bit lines, that one will discharge, and then you have a simple inverter to get the data out. This is how a read happens. Okay. So, yeah, so in the column you have a number of these memory cells and you have the word lines going horizontally, vertical is the bit line. So one of the, yeah, exactly. So you have say 128 word lines, you have a 7-bit decoder, it activates one of the 128 word lines. That word line goes high, the access devices are turned on, the bit lines which have been pre-charged and kept at 1 volt or at VDD, they discharge depending on which side of the memory cell is 0.
Suppose some level, they don't have connection, and both will be high. They don't put the bit and bit bar, they will not get discharge.
Correct.
So then I will get both. So information of output has to be taken from few both inputs.
Now, what happens is in this case, even you just have to look at one of the two, you will get the answer. Okay, you don't have to look at both. Now, if there is a problem where maybe this was 0 but there was an error, okay, that is the error. It's a malfunctioning memory cell. Okay, that's not good. So because you don't know, when both are high, you don't know which is the problem. Was it a 0 on the left side which was not disconnected, or was 0 on the right side which was disconnected? You can't make that out. So really there is no additional information by this pair of bit lines. But we'll see some other later on in one of the following lectures, certain other structures out here which can take advantage of this to give you differential operation and much higher speed access. Okay, we'll see that more from a circuit speed operation, not from redundancy operation. So that is as far as the read goes. Let's look at the write quickly. And in the case of the write, what you do is you remember that the NMOS is very poor at conducting a 1. It is good at passing a 0. So let us say in this example, okay, in this example Q bar is still 1. Now I want to, and Q 0, I want to write 1 to Q and 0 to Q bar. Now what you do is the bit line and bit bar are set up such that you have a 1 here and a 0 in the bit bar. Now if you look at the left side, when you have a 1 here in the bit and you have access device A1 and Q, this looks very much like the read case. It's like, that is what happens even in the read. In the read, this is 1 and Q is 0. Okay, and this starts discharging. But at the same time, if you look at this side, Q bar is 1 and bit bar is 0. So Q bar, starts discharging. Okay, now what happens usually is P1, P2 are the PMOS, they are weak. And this bit and bit bar are large capacitances. So, as current starts flowing out here, this voltage drops, Q bar starts dropping, because these are very weak transistors. As soon as some current goes, there is a large voltage drop set up. And when Q bar drops, this inverter Q starts going up, and then it reaches a certain critical point where it just flips. So you see, to do a write happens from the 0 side, where whichever bit line is 0, that one pushes the 0 in. So that is why when you read, you should not have the one of the bit lines 0, because that becomes like the write case, and you will flip the cell. Okay. Now this notion of being able to flip the cell or not being able, because sometimes if it's poorly designed, when you read, you can flip the cell. You will destroy the contents of the cell. So that is called instability, or it's unstable. Similarly, when you write, you fail to write. The cell is so strong that it doesn't overturn. So both of these are captured by what are called noise margins. Read noise margin, write noise margin. We'll kind of look at that in a later class. But basically, to do a write, what we do is in the column, very simple pull down structures based on the data. Either the bit or the bit bar is pulled down with a ending with a write signal. Only when write signal goes high, you pull down bit or bit bar, and then you write into the cell. Okay. For writing, you don't have to. You have to ensure that bit and bit bar, one of them is 1, the other is 0. Now, what is done out here is, either you can have a complete NAND gate out here, then the pulling up happens completely from the NAND gate, or what is done out here is the pull up is done through this precharge. It's the same, you precharge, then you pull down one or the other side with the data. So what all this does is it kind of adds to the timing control. You have to generate these signals which control all these different things. You have a small circuitry which is generating all these timing signals. So depending on, if you have very simple structures, or you can have very simple AND gate and so on, still get things done, but area overhead will be more. But when you do something more fancy, you will have to have a little bit more complicated control. Okay. But in the case of memory, area is always important. You really want as small area as possible. So whatever is done, you cannot do all this timing generation and so on in a separate place and generate all these signals. You can have it different. You can have it same. You can do both.
Whatever time take to charge and discharge. In the right case, I have additional circuitry which will add on my delays.
No, it turns out there are a lot of things that can happen in parallel. In the right case, see, because whether you do a read or write, you first have to decode and activate the word line. In the time it takes you to decode and activate the word line, what you do is you precharge. And when I want to do a read, I just precharge and leave it. When I want to do a write, I set up the data in the bit line. So that the decoding and setting up of the bit line happens in parallel.
So we can have write Q1 and similarly instead of that we can have read Q1 added to the pull-up structure. I mean we need any one, right, to control.
Yes. So if you do that, then for a write, because you have to also pull up the bit line to 1. One of the bit lines have to go to 1, the other has to go to 0. So then you need to put in the PMOS structure out here, which is duplicating the area. So that is why you kind of want to have a single precharge and a pull down happening either from the memory or from the write.